Welcome to the GeoMethod channel. Today we are solving another interesting geometry problem. Here is today's challenge. Can you find area of the green shaded quadrilateral? Take a moment to study the figure. Then let us uncover the two ideas that make the solution click. Here is right triangle ABC with its right angle at A. The green four-sided region ABED sits inside it, with D on the leg segment AC and E on the base segment BC. Our whole job is to find the area of that green quadrilateral ABED. We are handed only two lengths. The leg segment AB measures 8, and the inner segment DE measures 5. Every other length in this figure will have to be built out of just these two numbers, so let us keep them in front of us. The two tick marks on the base tell us segment BE equals segment EC, so E is the exact midpoint of segment BC. That means whatever length we call 1/2, the full base segment BC will be twice it, a fact we will lean on when Pythagoras arrives. The little square at E tells us segment DE runs left onto the base at a right angle, so the small triangle CDE is itself right-angled at E, and that right angle is going to pair up beautifully with the big one. The big triangle's right angle lives at vertex A, so leg segment AB and leg segment AC are perpendicular. That single right angle is the key that will later let the Pythagorean theorem tie the two legs to the hypotenuse segment BC. Here is the plan. The whole triangle ABC is made of two pieces, the green quadrilateral ABED and the small corner triangle CDE. So the green area is simply the whole triangle ABC minus that corner triangle CDE. Look closely at that second piece, the corner triangle CDE, tucked against the bottom end of the base. Its right angle sits at E, with one leg segment CE lying along the base and the other leg segment DE extending straight to the right. Pinning down this little triangle will unlock every length we need. Now, compare the corner triangle CDE with the big triangle CAB. They both contain the very same angle at C because it is literally the same corner of the figure. That is our first matching angle. They also each carry a right angle, the corner triangle at E and the big triangle at A. So a second pair of angles matches as well, both of them being 90 degrees. Aha! Triangle CDE and triangle CAB share the angle at C, while their LED corners at E and A are both right angles. Two right angles and the shared angle at C force similarity, so the 5-unit rail segment DE corresponds directly to the 8-unit rail segment AB. Lining the triangles up by that shared angle at C, the short leg segment DE corresponds to the long leg segment AB, and the base piece segment CE corresponds to the full leg segment CA. So segment DE over segment AB equals segment CE over segment CA. Let us give the unknowns names. Call each half of the base M, so segment CE equals M, and the whole base segment BC equals 2M. And call the leg segment CA by the letter B. Now pour the known numbers into the proportion. Segment DE is 5 and segment AB is 8, so the left side is 5 over 8, while the right side is M over B. That gives 5 over 8 equals M over B. Aha! Because E is the midpoint of segment BC, calling segment CE equal to M makes the whole base segment BC equal to 2M. Similarity simultaneously makes segment CA equal to 8M over 5. The midpoint and similarity express segment BC and segment CA using one scale M without revealing the final area. Time to use that right angle at A. The Pythagorean theorem on triangle ABC says the hypotenuse segment BC squared equals segment AB squared plus segment CA squared. This is the second equation that links our unknowns. Substitute what we know. Segment BC is 2m, segment AB is 8, and segment CA is 8m over 5. So 2m squared equals 8 squared plus the quantity 8m over 5 squared. Multiply both sides by 25 over 36 to free m squared. 64 times 25 is 1600 over 36, which reduces to 400 over 9. So m squared is 400 over 9. Take the positive square root, since m is a length. The square root of 400 is 20, and the square root of 9 is 3, so m equals 20 over 3. So segment CE equals 20 over 3, and the leg segment CA, which we found was 8/5 of m, becomes 8/5 times 20 over 3, which is 32 over 3. Now every length we need is known. Now the areas. The whole triangle ABC has perpendicular legs segment AB equal to 8 and segment CA equal to 32 over 3. So its area is 1/2 times 8 times 32 over 3, which is 128 over 3. The corner triangle CDE is right-angled at E with perpendicular legs segment CE equal to 20 over 3 and segment DE equal to 5. Its area is 1/2 times 20 over 3 times 5, which is 50 over 3. Finally, subtract. The green quadrilateral, ABED, is the whole triangle minus the corner. 128 over 3 minus 50 over 3, which is 78 over 3, and that simplifies cleanly to 26. So the answer is 26. So the final answer is 26. A good geometry problem often has more than one beautiful solution. If you see a genuinely different construction, a high-level idea that leads to another solution, or a thoughtful adaptation of an existing method, share the key idea in the comments. We greatly appreciate these contributions. With your permission, we may feature the approach in a future Viewer Solutions episode and acknowledge you by name or channel handle. Thanks for exploring geometry with GeoMethod.